Hey guys, so for today's video, in case it wasn't already obvious from the title, we will be covering exact equations and integrating factors. And first, so I have to explain what an exact equation is. So let's say we have um, some function of x and y that's called psi, and let's say that this is equal to some constant c. And let's say that y is also implicitly a function of x. So if we were to make a tree diagram, so we have psi, and psi is a function of x and y is a function of x. And since x is equal to x, x would also be a function of x. So yeah. Now, so first let's try taking the derivative of both sides with respect to x. And since c is just a constant, we can see that this would just be 0. And for this side, well, this would just be equal to the partial derivative of psi with respect to x times dx over x, which is just 1, plus the partial derivative of psi again, but this time with respect to y, times dy dx. And this would just be equal to partial derivative with respect to x plus the partial derivative of psi with respect to y times dy dx. And we can actually rewrite this to be in the form m of xy plus n of xy times y prime. And this would just be equal to 0. And so this equation here, or this expression, is considered exact if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And we can see why this is true for this to be exact using an identity from multivariable calculus. So if we go back here, we can see that m is just equal to the partial derivative of psi with respect to x, and n is just equal to the partial derivative of psi with respect to y. And there's this identity. It's known as I might be misspelling it, Clairaut's theorem, and it's taught in multivariable calculus. And what it basically states is that if you have any function, then and this function is, let's say it's a function of x and y, then the partial derivative like this is always equal to this one. Or in other words, if we want to put it in the fraction form, the partial derivative of x, or with respect to x, of del f del y is equal to the partial derivative with respect to y of del f del x. And so this, in essence, is precisely that. This is, since we said here that this is m and this is n, using this, we can see that this would just be equal to psi sub xy, and this would be equal to psi sub yx. And according to this identity, these two must be equal. Okay, so so now that I explained like the parameters for an equation like this to be exact, let's just do a practice problem. So I'm just gonna erase all this. Okay, so let's say I have some equation 2x plus 3y plus y times e to the power of xy, and this is added to 3x plus 4y plus x times e to the power of xy times y prime. And this is equal to 0. And let's say I need to verify that this is, actually I was going to verify exactness. So verify that this is exact and solve it, I guess. Okay, so, well, this would just be equal to m of xy, and this is equal to n of xy, and y prime is just the same thing as dy dx, since y is implicitly a function of x. Okay, and then as I said earlier, del m del y has to be the same thing as del n del x. So actually, let's first verify that it's exact. So del m del y is basically just the derivative of this, and you ignore the x, or you treat the x as a constant, since it's only with respect to y. And to do that, so we just get rid of this since it's constant, and we have 3 plus xy times e to the power of xy. And now we do the exact same thing for del n del x. And now we ignore the y. We treat the y as a constant. So we have 3 plus 2 and xy times e to the power of xy. So since these two are equal, this expression is indeed exact. Okay, now I have to solve for it. And to do that, since y is implicitly a function of x, we can't really write y in terms of x. So instead, we could write it in terms of psi. And so recall that m is just equal to del psi del x, and n is equal to del psi del y. Okay, and since this is exact, these two must be true. So then we can see that psi of x comma y is just the integral of m with respect to x. And yeah, so and m is just 2x plus 3y plus y times e to the power of xy dx. And since it's only with respect to x, once again we treat y as a constant. And so we have here x squared plus 3xy plus I believe that is y squared exy. Wait, let's double check this. Yeah. And yeah, but now there's also a constant. And since we're only integrating this with respect to x, the constant we actually write it as a function of y. Since we're treating y as constant and the constant is a constant, so we can say it's in terms of y. And so how do we solve for this? Well, we also know that n is equal to del psi del y. So let's actually find del psi del y. And now we treat x as a constant. So we have 3x plus 2xy exy plus h prime of y. And now let's look at the original. Wait, actually, okay, I believe there might have been a computational error somewhere. So let me just reintegrate this to verify that there are no mistakes. Um, okay, so x squared plus 3xy plus. Oh, okay, never mind. So this is actually just e to the power of xy plus. Okay, so yeah, same thing. So now, since we said that n is equal to del psi del y, so let's just take the partial derivative of this whole thing with respect to y. And we get 3x plus y times e to the power of xy. Wait, no, that's x times e to the power of xy. Okay, let me just. Okay, so 3x plus x times e to the power of xy plus h prime. And our original value of n was 3x plus 4y plus x times e to the power of xy. And so we can see that h prime is simply equal to 4y. And since h prime is simply equal to 4y, h is just the integral of that with respect to y. And so h is 2y squared, which means then that this is equal to x squared plus 3xy plus e to the power of xy plus 2y squared. And since at the beginning we said that this function psi is equal to some constant c, we just set this whole thing equal to c. So we have x squared plus 3xy plus e to the power of xy plus 2y squared. And we set this equal to c, and yeah, so that's basically it. And sometimes they'll give an initial value where you can actually solve for c, but not in this case. So this is the best that we can possibly solve it in this case. And yeah. Okay, now let's just, I'm just gonna erase this real quick. Oh shoot, okay, I did not know that the eraser erases the words. Oh well. Okay, so okay, so let's go back to our form. So we have m plus n y prime is equal to 0. Now in reality, this is actually rarely exact. So in other words, del m del y is not always equal to del n del x. And actually that's seldom the case. And this is where the integrating factor comes in. So we can actually make this exact if we multiply it to some integrating factor mu of x comma y. So this is the integrating factor. And yeah, However, determining when like mu exists, because it doesn't always exist, can be difficult. So instead of searching for mu in the form mu xy or mu of x and y, we can look for it either as mu of x or as mu of y, and you won't always find an integrating factor, so only sometimes. Sorry about that. Okay, so if let's say so there are actually formulas for the integrating factor. So mu of x is actually just equal to e to the power of. This is what x means, by the way. It just means e to the power of something. But e to the power of partial derivative of m with respect to y minus the partial derivative of n with respect to x over regular n with respect to x. And mu of y would just be equal to e to the power of, kind of the opposite now. So now it's um, the partial derivative of n with respect to x minus the partial derivative of m with respect to y over m. And yeah, so these are the general formulas. I'm not going to get into the derivation, but yeah, you just have to remember these when you want to find the integrating factor, if like this equation is not exact. And so, how do we know whether to use this or this? Well, if this expression here is a factor of x alone, then the integrating factor is in the form mu is equal to mu of x. And if this expression here is in the form of y alone, then mu is equal to mu of y. And yeah, so that's how you know which one to look for. And now let's just go over some practice problems to better illustrate that case. So let's okay, let's say we want to solve this equation here. So we have 2y over x plus 1 plus y squared over x squared times y prime, and this is equal to 0, and x is greater than 0. And we can already see that based on the form, this would be m, and this would be n, if they're exact. And I'll actually check right now to see if they're exact. Now, if they are exact, the integrating factor would just be 1, which means then that, so first let's actually do my minus mx over n. Okay, if we do this, we just get 2 over x minus negative, let's see, 2y squared over x cubed, and this is all over n, which is 1 plus y squared over x squared. And this is equal to 2 over x plus 2y squared over x cubed over 1 plus y squared over x squared. And we can see that we actually factor the top. And if we do that, we have 2 over x times 1 plus y squared over x squared over 1 plus, and as you can see, this is super convenient because we can just reduce this to 2 over x. And we can see that is this is only a function of x, and we know that our integrating factor would be only a function of x. And so we can just find our integrating factor using e to the power of 2 over x dx, which is the same thing as this, which is equal to e to the power of 2 times ln x. And using one of the identities for natural log is just the same thing as e to the power of the natural log of x squared, which is just x squared. Okay, so now we know our integrating factor, and so all we have to do is multiply this equation we started out with by x squared. So yeah, so that gives us 2xy plus x squared plus y squared times y prime is equal to 0. And because we already solved for the integrating factor and multiply that to the equation, we know that this has to be exact. And yeah. Okay, so this is m, and this is n, and by definition for an exact equation, we know that n is del psi del y, and m is del psi del x, by definition, since it's an exact equation. And now we can just simply do the same thing we did for the previous problem. So we can write that psi of x comma y is equal to the integral of m dx, which is just 2xy dx, which is just x squared y plus our constant, which since we're treating y like it's constant, we can say that it's a function of y. And boom. And now we can solve for what h of y is. Since we know that n is equal to x squared plus y squared, and we also know that n is equal to del psi del y, so we can just take the partial derivative of this with respect to y, and if we do that, so del psi del y. And that would simply be equal to x squared plus h prime. And so we can see then that h prime is y squared, which then implies that h as a function of y is the integral of y squared times dy, which is just y cubed over 3. So then we can write this back here, so then we get that psi of x comma y is x squared y plus y cubed over 3. And so to finally solve this, we get x squared y plus 1/3 y cubed is equal to c, where c is some constant. And yeah, so that's how you solve it using integrating factors. And yeah. And also one thing I should mention is sometimes you'll also get some equations like in the form, so you might get some equations in the form like m dx plus n dy is 0. And to solve these, all you have to do is just divide by dx. And if you do that, you'll see it'll just go back to the regular form. And you can solve it normally from there. So yeah, that's how you, that's what exact equations are, and that's how you use integrating factors to solve them. Or that's how you use integrating factors to make equations exact so that you can solve them. And yes, I hope that this video helped. And the next video will be on Euler's method and how you can use Euler's method to like approximate values of functions. So yeah.